Let's talk about VSEPR theory. VSEPR theory is the theory of chemical bonding that explains the geometry and bond angle of molecules. Geometry is the shape of molecules in three-dimensional axis, while the bond angle is the angle between three bonded atoms. VSEPR theory represents the molecules by the alphabetical notations A and B, where A is the central atom and B is the ligand atom. How many ligand atoms are attached with central atom? Their number is represented by X. Let's consider a real molecule of BeCl2, where beryllium is the central atom and chlorine is the ligand atom, and two chlorine atoms are attached with beryllium atom. So A is beryllium, B is chlorine, and X is 2 in this case. What is the geometry and bond angle of this beryllium chloride molecule? VSEPR theory explains it in detail. VSEPR stands for valence shell electron pair repulsion. As the name is indicating that valence shell electron pairs are involved in determining the geometry and bond angle of molecules. How many valence shell electron pairs are in beryllium? As beryllium is a central atom, so we are concerned with the valence shell electron pairs of beryllium. As beryllium has 4 electrons, and out of these 4 electrons, 2 electrons reside in the K shell and remaining 2 electrons reside in the L shell. As L shell is the outermost shell having the electrons, so this L shell is actually the valence shell and it is having the 2 electrons. The best possible conditions for 2 electrons around the beryllium atom is the position opposite to each other. And at this position, the repulsion between the 2 electrons is minimum, and this is the essence of VSEPR theory, that the valence shell electron pairs will determine the geometry and bond angle of molecules, and these electron pairs will occupy the position around the central atom so as to have the minimum repulsion, and at 180 degree at the opposite position around the beryllium atom, the repulsion between the 2 electrons is minimum. Same is the case with chlorine, which is 1 electron away from completing its octet and has the 7 electron in its valence shell. So it uses 1 electron to make a bond with beryllium atom. So 2 chlorine atoms make 1-1 bond with beryllium atom, resulting in BeCl2. As these 3 atoms are present in a line, the geometry of molecule is linear and the bond angle between Cl, Be and Cl is of 180 degree. This is how geometry and bond angle of molecule is determined. And for determining these two properties of the molecules, valence shell electron pairs are involved. These green colored lines are the bond pairs, as the electrons are shared between chlorine and beryllium in this case. So these are the bond pairs of electrons. Sometimes there are the central atom which are having the other electrons known as the lone pairs, and these lone pairs are not shared by the central atom with the any other atoms. These lone pairs will also affect the geometry of molecules, and in alphabetical notation these electrons are represented by E. E stands for lone pair of electrons. How many lone pairs are present on the central atom? Their number is represented by X at the subscript position of E. So based upon this alphabetical notation, there are many types of groups of molecules discussed by the VSEPR theory, but their main postulate is the valence shell electron pairs, either these are bond pairs or lone pairs, will determine the geometry of molecules, and they arrange themselves around the central atom so as to have the minimum repulsion. So this is the very first postulate of VSEPR theory. Let's write all of the postulates of VSEPR theory. The very first postulate, as I have told you earlier, is the valence electrons lone pair plus bond pair will determine the geometry and bond angle of molecule. The second postulate is lone pair will occupy a space around the central atom greater than the space occupied by the bond pairs. Why this is so? Because the lone pairs are attracted by the one atom only, and they are not as bound as the bond pair of electrons. The third postulate is lone pairs and bond pairs, as these are the electrons having negative charge, will repel each other, and the magnitude of repulsion is lone pair repulsion is greatest, then comes the lone pair bond pair repulsion, and then bond pair repulsion. The fourth postulate is the double bond or triple bond act as single bond. Their effect in determining the geometry is same as that of the single bond. However, as these are having the greater number of electrons in them than the single bond, so they occupy the more space. They occupy more space than the single bond. The fifth postulate is distorted geometry is due to the presence of lone pairs in a molecule. Its explanation will be discussed during the explanation of types of molecules that VSEPR theory encounters. There are other two postulates that will be discussed at the end of this theory. Anyhow, based upon these 5 postulates, let's talk about the types of molecules. AB2 type molecules have central atom joined with 2 ligand atoms, and I have told you earlier that the best possible condition for the 2 electrons around the central atom is to be placed at the 180 degree at the opposite side of central atom. AB2 type molecules have linear geometry and an angle of 180 degree. Examples are BeCl2. Same is the case with HgCl2. Other molecules are beryllium bromide, beryllium iodide, cadmium halides. This X can be chlorine, bromine, iodine. Another molecule which is AB2 type is carbon dioxide. As carbon has 4 electrons in its valence shell, an oxygen can make 2 bonds resulting in linear geometry and an angle of 180 degree. In addition to the neutral molecules, there are certain ions that are of AB2 types. These include nitronium ion. This nitronium has nitrogen with 1 positive charge. Experiments show that nitrogen does not have lone pair in this molecule. Nitrogen has 5 electrons in its valence shell, and it is making bond with 2 oxygen atoms. Oxygen is making double bond with nitrogen using It's 2 electrons and 2 electrons of nitrogen. Same is the case with other oxygen atom. Both of these oxygen are neutral because they are utilizing their normal oxidation state, while the experiments prove that nitrogen in this case is having the positive charge. Its geometry is also linear and the bond angle is of 180 degree. So the AB2 type molecules have linear geometry, no lone pair and 180 degree bond angle. There are certain molecules that are having the central atom attached with 3 ligand atoms. These are known as the AB3 type molecules. Their examples are
boron trihalide,
where X is a halogen atom. 3 electrons in the valence shell can be arranged around the central atom like this, and at this position they are having the minimum repulsion. Boron is making 3 bonds with 3 halogen atoms, and halogens can make 1 bond. This is the possible bonding formation pattern. This kind of geometry is trigonal planar geometry, and a bond angle between X, boron and X is 120 degree. The other molecules of AB3 types are formaldehyde, where central atom is carbon, that can make 4 bonds. As carbon is joined with 2 hydrogen and 1 oxygen atom, hydrogen can make 1 bond with carbon, single bond with carbon, and oxygen can make double bond with carbon. So carbon is utilizing all of its 4 valence electrons, resulting in a geometry known as trigonal planar, and their bond angle is of 120 degree. Another molecule of this type is sulfur trioxide. Sulfur has 6 electrons in its valence shell. How many electrons in the valence shell of an atom are there? You have to calculate by yourself. Do not just rely on cramming this stuff, just practice it by yourself. As sulfur is having 6 electrons, why it is having 6 electrons? You have to find out that using the method I have discussed at the start of the lecture. So 3 oxygen atoms are arranged around the sulfur atoms, and they are making double bond with sulfur, and this kind of geometry is trigonal planar with bond angle of 120 degree. AB2 types have 1 lone pair. Examples are sulfur dioxide. As I have discussed earlier, that sulfur has 6 electrons in its valence shell. Sulfur and oxygen will make 2 bonds, and the 1 electron pair will be a lone pair on the sulfur. As there is a lone pair on the sulfur, this lone pair will repel the bond pairs of oxygen and sulfur, and this repulsion will result in closure of double bond of oxygen and sulfur, resulting in decrease in bond angle. This kind of geometry is V-shaped, bond angle less than 120 degree. Why they have bond angle less than 120 degree? It is because the lone pairs repel the bond pairs. This repulsion will result in degrees of bond angle. Now we have discussed 3 to 4 examples where there are double bonds, but they do not affect the geometry of molecules. Boron trifluoride having a single bond has trigonal planar geometry. Sulfur trioxide has all double bonds, but its geometry is trigonal planar. So double bonds will not affect the geometry of molecules. However, they occupy the space greater than single bond, SnCl2, where Sn has 1 lone pair. The bond angle is less than 120 degree and its geometry is V-shaped or angular. Now let's talk about AB4 type molecules. In AB4 type molecules, the central atom is surrounded by the 4 electron pairs, and all of these are bond pairs. None of the lone pair is present in AB4 type molecules. The examples include carbon tetrachloride. Carbon can make 4 bonds. Chlorine can make 1 bond. So carbon will make 4 single bonds with 4 chlorine atoms, resulting in a geometry known as tetrahedral geometry. The bond angle between chlorine, carbon and chlorine is of 109.5 degree. So AB4 type molecules have geometry tetrahedral and bond angle 109.5 degree. Other examples include methane,
silicon tetrafluoride, tetrafluoroborate.
You have to practice it by yourself. This is a practice question for you. CF4, ClO4, negative. Let's talk about the AB4 type molecules but having one lone pair. These include AB3 type molecules. And this is showing that central atom is having 4 electron pair around itself, where 3 are bond pairs and 1 is
ammonia,
where nitrogen is having 1 lone pair. So best possible orientation of electrons is like this. As you see that there are the lone pairs on central atom. These lone pairs will repel the bond pair and bond pair come close to each other and the bond angle will decrease. So AB3 type molecules will have bond angle less than 109.5 degree. Why? Because they have one lone pair and lone pair will repel bond pair, resulting in decrease of bond angle. So the geometry is trigonal pyramidal. The other molecules of AB3 type are
phosphorus trichloride,
AsCl3 and PH3. For the better understanding of VSEPR theory, you have to practice and determine the geometry of these 3 molecules by yourself. Now there is another possibility that AB4 type molecules have 2 bond pair and 2 lone pair, and these kind of molecules are AB2 type. For example,
water, hydrogen sulfide, nitrous oxide, dichloromonoxide.
As this oxygen has 6 electrons in valence shell, so here is a single bond made by the 2 hydrogen atom. Remaining are 4 electrons that will be the lone pair. As there are 2 lone pairs on oxygen atom, so they will exert more repulsion towards the bond pair and the bond pair come closer to each other and the bond angle will decrease. These kind of molecules have also bond angle less than 109.5 degree. The original 109.5 degree is for AB4 type molecules with 0 lone pair. Whenever a lone pair is increased on the central atom, the original bond angle will decrease. Same is the case with H2S, N2O, Cl2O. Let's discuss N2O, where nitrogen and oxygen are bonded. Oxygen having 2 lone pair and making 1 bond with 2 nitrogen atoms, and nitrogen is having 2 lone pairs. The lone pairs of ligand atom will not affect the geometry, but the lone pair on the central atom will affect the geometry of molecules. The geometry of AB2 type of molecule is bent or angular. Up till now we have discussed AB2, AB3, AB4 type molecules. Now let's talk about AB5 type molecules, where central atom is surrounded by 5 pair of electrons. The examples include
phosphorus pentachloride, phosphorus pentafluoride, antimony pentachloride, arsenic pentachloride.
5. You have to practice all of these. I will tell you about the geometry and bond angle in PCl5. Phosphorus has 5 electrons in its valence shell that are making 5 bonds with 5 chlorine atoms. So phosphorus is making 5 bonds, 1, 2, 3, 4 and 5. The best possible condition for the arrangement of 5 electrons around the central atom is like this, where phosphorus is making 5 bonds with 5 chlorine atoms. This kind of geometry is known as trigonal bipyramidal. So AB5 type molecules have geometry trigonal bipyramidal. Where there are two types of atoms. The atoms making a triangle are at equatorial position, E position. So in AB5 type molecules there are 3 equatorial position and 2 axial positions. And the axial bonds are different from equatorial bonds. This is proof experimentally that the decomposition of phosphorus pentachloride results in phosphorus trichloride plus chlorine gas, which is showing that 2 chlorine atoms are different from 3 chlorine atoms. The bond between 2 axial positions is of 180 degree. Between 2 equatorial position is of 120 degree, and between 1 axial and 1 equatorial position the bond angle is of 90 degree. So there are 3 types of bond angles in AB5 type molecules. Now let's discuss AB5 type molecules but having one lone pair, which are regarded as AB4 type molecules. Central atom is surrounded by 5 electron pairs, where 4 are bond pairs and 1 is lone pair. Examples include
Sulfur tetrafluoride, tellurium tetrafluoride.
Let's talk about the geometry of sulfur tetrafluoride. Sulfur has 6 electrons in its valence shell, but it is making 4 bonds, which means the 2 electrons will be the lone pair. Where there will be the lone pair? At axial or at equatorial position. Experiments show that the lone pair will be at the equatorial position. As there is a lone pair in the molecule, the bond angle between the equatorial positions will be decreased, and it is less than 120 degree, and in the case of SF4 the bond angle between 2 equatorial atoms F, sulfur and fluorine is of 116 degree. The geometry of AB4 type molecule is seesaw. In addition to AB4 type molecule, there is a possibility that central atom can have 2 lone pair. These kind of molecule are AB3 type molecules. Central atom is having 3 bond pairs and 2 lone pairs. Examples of these kind of molecules include
Chlorine trifluoride, bromine trifluoride.
the interhalogens. Bromine is a central atom surrounded by 3 fluorine atoms. As bromine has 7 electrons in its valence shell and is making 3 bonds, so 4 of its electrons are not bonded, which means there are 2 lone pairs on bromine and lone pairs are on the equatorial positions. one fluorine, second and third. The angle between the two axial fluorines is 175 degree, is less than 180 degree because of the presence of lone pairs. The geometry of AB3 type molecules is T-shaped. You have to practice the geometry of ClF3 by yourself. Let's talk about AB2 type molecules, which means central atom is having 2 bond pairs and 3 lone pairs. And central atom is surrounded by 5 electron pairs on the whole. Examples include xenon difluoride. As xenon is surrounded by 8 electrons, its valence shell contains 8 electrons. It is bonded with 2 fluorine atoms. So 2 out of 8 electrons are bond pairs. Remaining are 6 electrons, which are divided into 3 lone pairs. So 3 lone pairs and 2 bond pairs show that it is an AB5 type molecules but having 3 lone pairs, so it is actually the AB2 type molecules. Lone pairs will be at the equatorial positions and axial positions contain bond pair. Its geometry is linear. Let's talk about AB6 type molecule. The central atom is surrounded by the 6 electron pairs. Example include SF6. Sulfur has 6 electrons in its outermost shell. If all are the bonded, then the arrangement of electron around the central atom would be like this. Geometry of AB6 type molecule is octahedral. All of the fluorine in SF6 are identical and the bond angle between adjacent two fluorines is of 90 degree and the bond angle between two opposite fluorines is of 180 degree. Other examples include PCl6 negative, as phosphorus can make 5 bonds but now it is making 6 bonds. Let's discuss its geometry. Phosphorus can have 5 bonds, 1, 2, 3, 4, 5, but in this ion it is making 6 bonds, which means it has added up one extra electron in its outermost shell and has the negative charge. So this is how it is making 6 bonds. Moving further, if AB6 type molecules have one lone pair, these molecules will be AB5 type molecules. An example include
bromine pentafluoride, iodine pentafluoride,
SpCl5 2 negative. This is an ion, and try to practice the ions by yourself to better understand the VSEPR theory. Let's discuss the geometry of IF5, where iodine has
tetrafluoroborate,
making 5 bonds, which means
carbon tetrafluoride,
electrons are remaining on the iodine atom, and these are the lone pairs 1, 2, 3, 4, 5, and this is the lone pair. 5 fluorine atoms are bonded with the iodine. The geometry of AB5 type molecule is square pyramidal. Or tetragonal pyramidal. If the AB6 type molecules have 2 lone pairs, these kind of molecules will be AB4 type molecules. which means these are having 4 bond pairs and 2 lone pairs. Examples include xenon, tetrafluoride,
tetrafluoroiodate, tetrafluorobromate.
Let's talk about the geometry of this ion. Iodine has 7 electrons in its valence shell. It is making 4 bonds, which means it is having 3 electrons non-bonded. Let's say 1, 2, 3, 4. This is one lone pair and this one electron is single. Let's draw the bonds first. Cl, Cl, Cl and chlorine. This electron is unpaired, but you see the negative charge on this ion, which means iodine has accepted one electron more and this is acting as a lone pair. The geometry of this kind of molecule is square planar.
The AB7 type of molecules have 7 electron pairs around the central atom. The examples include iodine heptafluoride, where the central atom is iodine that has 7 electrons in its valence shell. The 7 electrons around iodine can be arranged like this. This arrangement shows the possible orientation of electrons around the iodine so as to minimize the repulsion between them. These electrons make 7 bonds with 7 fluorine atoms, creating 7 single bonds in iodine heptafluoride molecule. The geometry of iodine heptafluoride is pentagonal bipyramidal. There are 2 types of fluorine atoms in iodine heptafluoride. These 2 fluorine atoms are known as the axial fluorine atoms, while the remaining 5 fluorine atoms are the pentagonal planar atoms. These 5 fluorine atoms are Fb atoms that are making the vertices of a pentagon. Therefore, these are the pentagonal planar atoms, while the remaining 2 fluorine atoms are the axial fluorines. The bond angle between 2 axial fluorine atoms is of 180 degrees, and the bond angle between one axial and one pentagonal planar fluorine atom is of 90 degrees. The bond angle between 2 fluorine atoms belonging to pentagonal planar is of 72 degrees.
However, there is a drawback in VSEPR theory. VSEPR theory successfully explains the geometry and bond angle of a molecule, but it doesn't tell us about how the electrons are shared, what happens between the 2 atoms and the electrons get shared, how the bonds are formed. Moreover, it doesn't let us predict the bond length and bond energy of the molecules. The geometry and bond angle of all of the molecule was based upon the 5 postulates that we discussed earlier during the lecture. I told you earlier that there are the 2 postulates that we will discuss at the end of this lecture. These 2 postulates are bond pair influence decreases when electronegativity increases. Now what is this? Let's consider 3 molecules Pi3, PBr3, PCl3. Phosphorus triiodide, phosphorus tribromide, phosphorus trichloride. These all are AB3 type molecules. Central atom is having 4 electron pair around itself, where 1 is lone pair and 3 are the bond pairs. The bond angle between iodine, phosphorus and iodine is of 120 degree. Between bromine, phosphorus and bromine is of 101.5 degree, and in the case of PCl3 bond angle is of 100 degree. All of the three molecules have same geometry, but their bond angle is different. Why it is happening? It is happening because the electronegativity of iodine is less than the bromine, and bromine has the electronegativity than the chlorine. Whenever the electronegativity increases, the bond angle decreases. This is because chlorine will attract the bond pair towards itself, and the probability of bond pair closer to the phosphorus decreases, giving more room to the lone pair to expand around the central atom, resulting in closure of bond pairs and ultimately decreasing the bond angle. That's why phosphorus is having the greatest bond angle, where iodine is the least electronegative. The seventh postulate is repulsion between bond pairs of completely filled shells is high. For example, H2O and H2S both have bent geometry, but the bond angle of water is 105.5 degree and the bond angle of H2S is 92 degree. Why? Because water has central atom oxygen and H2S has central atom sulfur. The valence shell of oxygen in water is completely filled, so its bond pair will offer greater repulsion to each other. They expand, move away from each other, and bond angle will increase. On the other hand, in H2S, hydrogen sulfide gas, the valence shell of sulfur is not completely filled. Its d orbital is completely vacant. Its bond pair will not repel so much. They are relatively closer to each other and their bond angle decreases up to 92 degree. This was all about the postulates and rules of VSEPR theory and the types of molecules explained using the VSEPR theory. However, VSEPR theory has certain drawbacks. It doesn't tell us that what happens between two atoms during bond formation, how the electrons are shared. It doesn't talk about the orbitals. It doesn't talk about how the bonds form, where the bonds form. Also, it doesn't let us know about the bond lengths and bond energies. Therefore, to explain how the bonds are formed, what happens during chemical bonding between two atoms and the two atoms share the electrons ultimately. This phenomena is explained by VBT and MOT using the quantum mechanics wave model of the atom and the concept of orbitals. These two theories, VBT and MOT, talk about the orbital and use broadly the concept of overlapping of orbitals during the bond formation. However, VSEPR theory successfully explains the geometry and bond angle of molecules. Stay tuned for the upcoming sessions on VBT and MOT. Thanks for watching.